Now we're going to talk about carbon-oxygen double bond containing functional groups. And these are called carbonyl groups. That's an oxygen double bonded to a carbon. Example is shown right here. And that carbon then has two more bonds. It can form bonds with an R group, like a carbon or a heteroatom, and a different R group. So typically there'll be carbons here, but we'll also see examples where an H might be bound to this carbonyl, an O, an S, or an N. And these are a component of many different functional groups. So this in itself is not a functional group. It's part of many different functional groups. So several carbonyl containing functional groups are shown here. Aldehydes have R on one side, H on the other side. Ketones have R groups on both sides of the carbonyl. A carboxylic acid has an R on one side and an OH on the other side. Ester has R on one side, OR group on the other side. And a thioester has, instead of an OR, has an SR, and an amide, different from an amine, has an R on one side of the carbonyl and an N with two bonds on the other side, and these bonds could be H or R. Both are considered amides. So remember in our discussion of molecular geometry, this carbon has three molecular groups surrounding it. Two single bonds, one double bond, so its geometry is trigonal planar. It's two-dimensional. And remember also that the CO double bond is polar, so it interacts well with other polar compounds. This oxygen draws electron density towards itself from the carbon. And this means that many carbonyl compounds can be soluble to some extent in water. They are polar, water's polar, like dissolves like. The simplest type of carbonyl compound are typically aldehydes. They are carbonyls with hydrogen and some other group attached to the other side. The simplest aldehyde is called formaldehyde. It actually has two H's attached to this carbonyl group. Its IUPAC name is methanal because it's derived from a one-carbon methane. Al at the end of the name to indicate aldehyde. The next simplest aldehyde is called ethanal. It's a carbon with a methyl group on one side and a hydrogen on the other side. It's an aldehyde derived from two carbons, so the root is ethane, and we change it from ANE to ANAL. Propanol is the three-carbon aldehyde. Has three carbons, one has the carbonyl, and two form this ethyl group on one side of the carbonyl and the H on the other. Cinnamaldehyde is a natural product. It smells like cinnamon. It has an aldehyde functional group, and it's also indicated by its common name, cinnamaldehyde. Here's a review from section 7.1. What is the correct IUPAC name for the following alcohol? So remember, for naming alcohols, we first identify the main chain, the longest carbon chain that possesses the alcohol. In this case, there is only one long carbon chain, 1, 2, 3, 4, 5. 5 carbons is pentane. Change that to pentanol because we have an alcohol group. And we start numbering at the carbon, or the end of the chain nearest to the substituent. I think we recognize that it's in the middle of this 5 carbon chain, so it doesn't matter, but it gets carbon number 3. So 3-pentanol is the best choice here. A ketone is different from an aldehyde in that it has two R groups on either side of the carbonyl instead of one R group and one H. The simplest ketone is the 3-carbon ketone, has two methyl groups on either side of the carbonyl. The IUPAC name is 2-propanone, commonly known as acetone. This is in nail polish remover. And so you can see how we name this carbon, or this molecule. We start with a 3-carbon chain, propane. We change the ANE to ANONE to indicate that it is a ketone. ONE indicates ketone. And we also provide a number indicating where the ketone is along the main chain. In this case, it's on carbon number 2. Here's 2-pentanone, a 5-carbon ketone. It has a methyl group on one side, a 3-carbon group on the other side. The ketone is located on the 2-carbon, so we call it 2-pentanone, derived from pentane. We can also have 3-pentanone, where the ketone is on the 3rd carbon end. Again, derived from pentane, except that now the ketone is on the 3rd carbon. So let's do some practice problems in naming the following aldehydes and ketones. So this is an aldehyde. There's an H and an R group over here, so it's called an aldehyde. It starts with 3 carbons, so we start with propane. We change the ANE to ANAL to indicate that it's an aldehyde. And since the aldehyde can only reside on the end carbon, we don't need to provide a number indicating where the aldehyde is. It can only ever be on the end because it has to have an H on one side of it. So this is the name, propanal. This molecule has a ketone functional group here. One, two, three, 4, 5, 6, 7, 8 carbons in the chain, octane. And the ketone carbon is on carbon number 3. So we call this octanone, ONE to indicate that it is a ketone. We put a 3 to indicate that the ketone is on carbon number 3 from the end of the chain. We don't start numbering from this side because we'd have a much larger number. So we want to keep this number as small as possible. So 3-octanone. 3 tells us where the ketone is. ONE tells us we have a ketone. And oct, or octanone, tells us we have an 8-carbon chain. This is also a ketone. This carbon chain now is a 6-membered ring, cyclohexane. So cyclohex, ANE turns into ANONE, cyclohexanone. We change the E to ONE. We don't need to put a 1 because the ketone, if it's the only substituent, it can go on any of these carbons and you'll agree that we have the same molecule. So the 1 is ambiguous. Or superfluous, I should say. This next structure here, 1, 2, 3, 4 carbons in a chain, that's butane. And this functional group is an aldehyde. It's a carbonyl with an H and a carbon. And so we change ANE to ANAL, butanal. Butanal. Al for aldehyde. And lastly, we've seen this one again before, a 3-carbon propane. We can change propane to propanone. To indicate there's a ketone present, and it is on the 2nd carbon, so 2-propanone. That's how we name that one, or acetone. But if we're looking for the proper IUPAC name, that's 2-propanone. The next part says one form of the sugar glucose is shown here. Circle the aldehyde functional group in this molecule. Now here we didn't explicitly draw it out, but I think we can recognize that this is an alcohol, 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 alcohol. So this is the aldehyde. That's an abbreviation of C double bond O H, CHO. So that's an abbreviated version of actually writing out the aldehyde structure here. What other functional group is present? Well, certainly we see lots of alcohol groups. And as we said before, sugars are notorious for having lots of alcohol functional groups. That's why they're very soluble in water. Okay, now we want to discuss carboxylic acids. So they have this general structure, carbonyl with an R group and an OH group attached to it. Please note that this is not an alcohol group because it is attached directly to a carbonyl. Don't confuse this with an alcohol group. This entire group here is a carboxylic acid. The simplest carboxylic acid is derived from 1 carbon. It's called methanoic acid, or commonly formic acid. Methanoic because it's derived from 1 carbon. We change methane into oic acid. We take off the ANE, we put ANOIC acid. So this is methanoic acid. Notice we highlight the entire C double bond O OH group as the carboxylic acid group. A 2-carbon carboxylic acid derived from ethane turns into ethanoic acid. It's also commonly known as acetic acid. That's one of the components of vinegar. 3-carbon chain, propanoic acid. Notice we aren't putting 1s here to indicate where the acid is because it has to be on the end. It can have a carbon chain on one side, but the other side has to be an OH. So this is always the end of a molecule. And then if we have a carboxylic acid attached to a benzene ring, we call that benzoic acid. An interesting thing about carboxylic acids is that they might lose a proton, H+, in solution to form a carboxylate ion. And the name of the ion ends in ate ion. So first off, why is this called a proton? Well, this is an ionized hydrogen atom. If we refer back to the periodic table, remember that hydrogen is in group 1a, period 1. It is atomic number 1, so it has 1 proton and 1 electron. And we can observe that its atomic mass is just about 1, which tells us that on average a hydrogen atom is composed entirely of 1 proton and 1 electron. It does not have any neutrons. And so if we take that electron away to make it ionized H+, all we're left with is 1 proton. So chemists will often call the H+ ion a proton. So if you hear me refer to a proton when we're dealing with organic chemistry, I'm commonly talking about the H+ ion. And so if we look at a generic carboxylic acid here, RC double bond O, OH, this proton here is reasonably acidic, and it can be lost to form a proton and what's called a carboxylate ion, the ionic form. And this is a negative charge because we lost a positive proton. Negative plus positive equals 0 over here. And so we can ionize carboxylic acids to produce their carboxylate ion and a proton. And the carboxylate ion is an example of a polyatomic ion. Remember the acetate ion, CH3COO-, that's shown here, that's a polyatomic ion. And typically they will exist together with a cation to form an ionic compound. This is called sodium acetate right here. And you could think of this very similar to sodium chloride, where we have a sodium plus and we have an anion. Certainly it's not a chloride, but it is still a piece of the ionic compound that has a negative charge. And these carboxylate ions, as you might have guessed, are much more soluble in water. That's because they have a full negative charge. They're charged. That means they're much more polar than a normal uncharged molecule. And we know that salt is an ionic species. It dissolves readily in water. So does sodium acetate. So carboxylate ions are much more soluble in water. Carboxylic acids, when they have their OH present, easily form hydrogen bonds with water or other similar compounds because they have an OH bond. Here's an example of 2 carboxylic acids hydrogen bonding with each other. We can see they form 2 hydrogen bonds, one from the OH on one molecule and the carbonyl oxygen on the other, and then the second OH and the first carbonyl oxygen. So they form what's called a dimer here between 2 carboxylic acids. And if the R group is small enough, these carboxylic acids can be soluble in water. We know that acetic acid, where R equals CH3, a methyl group, is very soluble in water. If R has 7, 8, 10 carbons in it, it's going to be much less soluble in water because there'll be a lot of carbons for only the one OH group. And these hydrogen bonds between either between carboxylic acids can increase the melting point and the boiling point. They increase the strength of the intermolecular forces. Therefore, the energy required to melt or boil a compound is increased. So a fatty acid, which you might be familiar with that term, are long hydrocarbon chains containing the carboxylic acid group. So here's a fatty acid. We see a long hydrocarbon chain with a carboxylic acid on the end. And in order to make a soap, we will deprotonate, remove this H here, to form a carboxylate ion from that same fatty acid. Now we have a highly charged polar head group and a nonpolar tail. And we can see that when we use this soap to wash grease off of our hands or off of our clothes, grease is very nonpolar as well. So like dissolves like. The grease will interact with this nonpolar tail of the molecule, and the water, which is polar, will interact with this highly charged polar head group. And so we'll be able to form micelles, such as shown here in the image, with the grease in the middle, surrounded by the nonpolar tails of the carboxylate ion, and the polar head groups are on the outside of this micelle, interacting with the water. So we can essentially dissolve the grease off of our clothes or our hands and get it into water where we can wash it into the sewer. Let's look at question 7.5. What type of functional group is shown in this drawing here? Okay, so we can recognize the carbonyl species. That narrows it down. and there are 2 R groups on either side of that carbonyl species, and that fits the definition of a ketone. Turns out that we can take a carboxylic acid and make many other functional groups from that carboxylic acid, and those are called carboxylic acid derivatives. They resemble carboxylic acids because they have a carbonyl and they have a heteroatom connected to that carbonyl. Not an OH, but an OR, SR, or NH, or NR. So these are carboxylic acid derivatives because they are very similar to a carboxylic acid in that they have a carbonyl with a heteroatom attached. First one we want to discuss are esters, and that's where an OR will replace an OH. So here's an example of aspirin. That has a carboxylic acid functional group, and it also has an ester functional group. Here's a carbonyl, an R group, O, R group. So the entire rest of the molecule is the R group for this ester. So this is an ester, a carbonyl, OR. Triglycerides found in fats contain the ester group as well. Carbonyls, R groups, long hydrocarbon chains, and OR. It doesn't matter what's beyond the first carbon in that group. Everything here is considered part of the OR group for this ester. Same thing for this ester. This is an OR group. OR group. In naming esters, we'll follow the patterns used with other organic compounds, typically assigning the root, the number of carbons in the longest continuous chain that includes the carbonyl carbon. Then we assign the suffix. We change, say, butane to butanoate. So we take off the E, we add OATE. That's to indicate that it is an ester. 1 and 2 carbon chains are often named formate and acetate just by convention. And then we assign the prefix, which is typically the R group on the oxygen. We name it in the same manner as other substituents, methyl, ethyl, propyl, etc. So here are some examples of common esters. This ester has 2 carbons in its chain containing the carbonyl. So that gets the root ethane. We change it to ethanoate and indicate that the R group is methyl. So we label it methyl ethanoate. Ethanoate, 2 carbons containing the carbonyl, a 1 carbon R group. Here again, 2 carbons containing the carbonyl, a 2 carbon R group. That's called ethyl ethanoate. And here we have 3 carbons in the chain containing the carbonyl. That gets propanoate. Starts from propane, changed to propanoate. And we have a methyl group attached to the OR, or as the OR, so it's methyl propanoate. Typically there's a space between the R and the ester root. Ethyl space ethanoate. So here we have an example of a drug. Flutokinase propionate is the active pharmaceutical ingredient in Flonase nasal spray. We want to circle and label the thioester and the ester functional groups and explain how they are different. So remember that the thioester, we're looking for SR next to a carbonyl. SR next to a carbonyl. There's only a few carbonyls in the molecule. Here's a carbonyl. Here's a carbonyl. And here's a carbonyl. Which one has an SR group attached to it? Well, I think we'll recognize that it's this carbonyl that has an SR group, and that's thioester. So then the ester has an OR group attached to it. This carbonyl has an oxygen, and the entire rest of the molecule is the OR group, so we'll call this one the ester. Circle and label the ketones and alcohol functional groups in the molecule. Well, ketones are also derived from carbonyls. This is a ketone. And alcohol functional groups, again, those have OHs, which are not next to carbonyls. This is an alcohol. And I don't see any other alcohols present. So we've labeled the alcohols, the ketone, the ester, and the thioester. What is the proper name of the compound shown in this image? So remember that we first start by naming the main chain containing the carbonyl. So that'll be this 4-carbon chain. And we start with butane. We change it to butanoate because it is an ester, butanoate. And then we name the R group as a substituent. 2 carbons, ethane changes to ethyl, ethyl butanoate. That's answer D is the best choice here. So another form of carbonyl derivative, carboxylic acid derivative is called an amide. These are different from amines. We'll talk about amines in a few minutes. So amides have a carbonyl with an R group on one side and a nitrogen with either H's or R's attached to it. So these are all examples of amides. They can have hydrogens or R groups attached, and the nitrogen is directly attached to a carbonyl. That's an amide. So this entire section is an amide. The carbonyl and the N behave as a single unit. That's an amide functional group. Proteins and oligopeptides contain the amide group, and they're great examples of amides. The drug penicillin is also an amide. Here's penicillin. We see a cyclic amide right here. We have an oxygen a carbonyl bound directly to a nitrogen, and that nitrogen has 2 R groups attached to it. Here we have a carbonyl bound directly to a nitrogen with an H and an R group. And this amine here in blue is not an amide because it is not bound to a carbonyl. It's attached simply to an R group. Here is a short oligopeptide. It has 4 amide groups in it. So here's a carbonyl, NHR. Here's a carbonyl with an NHR group on it. Carbonyl attached to an N, carbonyl attached to an N. So we see that there are many amides present in this oligopeptide. Some more practice problems. Which of the following structures is an amide functional group? So we just got done discussing amide functional groups. We know that an amide is going to be a nitrogen directly attached to a carbonyl, so this is an amide functional group here. We have the nitrogen directly attached to the carbonyl. Doesn't matter what these are, could be H's, could be R's. What's the name of this functional group here? Right, this is an ester group. How about this one? What's the name of this functional group? Carboxylic acid. And this last one, this differs from the ester only in that we change this O into a sulfur, so this is a thioester. The structure of vitamin B5 is shown below. Circle and identify the functional groups. Okay, so functional groups can be identified simply by having heteroatoms. So all we have to do is identify every place there's a heteroatom. Here's one place. That's an acid or a carboxylic acid. Another heteroatom is down here. This is an OH bound to an R group. That's simply an alcohol. Here is another OH bound to an R group, so that is also an alcohol. Here's a carbonyl. It's got an R and a nitrogen. So we circle the entire carbonyl nitrogen, and that, as we just learned, is an amide. The entire carbonyl nitrogen structure. Clicker question 7.7. Some more practice identifying functional groups. What functional groups can you identify in the structure of Lipitor shown below? Again, we should look for heteroatoms to indicate where functional groups might be located. Here's heteroatoms. This is a carbonyl attached to an OH group. This is a carboxylic acid group. Here's some heteroatoms. They're simply attached to R groups, so these are both alcohols. Here's a heteroatom. We haven't learned what this is yet, so we can't identify it. Here's a heteroatom, oxygen, doubly bound to a carbon, attached to a nitrogen. This is a amide functional group. These are aromatic functional groups, which we typically don't list off, but we can describe them at least. This is a fluorine or a halogen functional group, and these could be considered alkenes. So we have alcohol, we have a carboxylic acid and an alcohol. We have an amide, so we need one that has all three. That is answer D, carboxylic acid, amide, and alcohol.